alkylation of an enolate ion. Adding an alkyl group to the alpha position of the carbonyl compound is an extremely useful reaction in synthetic organic chemistry because it leads to the formation of a carbon-carbon single bond. Now, how are we going to do the alkylation of carbonyl compound? For this, we have to first synthesize the enolate ion. The enolate ion can be synthesized by a regular method where we are going to use LDA and use THF as a solvent at minus 78 degrees Celsius. Right? So this is going to give us enolate ion, and the enolate ion will be in resonance stabilized. For now, we are going to write only the resonance contributor where there is a negative charge on carbon. So the LDA will go and abstract one of these hydrogens, right, and thrust these electrons onto carbon. So this is our enolate ion. Now in the next step, we are going to do a typical SN2 reaction where this enolate ion is going to act as a nucleophile on an alkyl halide. Now depending upon the number of carbons that you want in this, want to get attached to this alpha carbon, you can choose the alkyl halide. If you want to put an ethyl group, obviously you're going to choose ethyl bromide or any ethyl halide, right? So you're going to react it with alkyl halide, where this nucleophilic carbon will go and make a nucleophilic attack on this electrophilic carbon of alkyl halide and thrust these electrons onto the leaving group for it to leave. Here is a product obtained, and you can see that the hydrogen has now been substituted for the alkyl group. We can also use this reaction for alkylating the alpha carbon of esters and as well as nitriles. Now for this reaction, the alkylation of carbonyl compounds on the alpha carbon, instead of LDA, if you're going to use hydroxide ion as a base, then it's going to form polyalkylated products. Since hydroxide ion is a weaker base, it's going to form the enolate ion from the monoalkylated products. Say for example, we do have alpha hydrogens here even. So these alpha hydrogens will be abstracted by the hydroxide ion, and it's going to form the disubstituted, trisubstituted, and even the tetrasubstituted products. Using exactly the same method, we can also alkylate esters and nitriles at the alpha carbon. So here are some examples. You can see that this is an ester molecule, right? And we'll find the alpha carbon. So this is our alpha carbon, and one of these hydrogens right here has been replaced by an methyl group. And here again, this is our alpha carbon. One of these hydrogens have been replaced by an ethyl group. So we can conveniently use this method to alkylate even the esters and nitriles. When you do the alkylation on an unsymmetrical ketone, then it has the ability to form more than one product. And the product distribution is going to depend on the condition that we apply for the reaction. Let's do this with 2-methyl-cyclohexanone. When 2-methyl-cyclohexanone is reacted with LDA, obviously it will give us the enolate ion. But here in this case, it's going to give us two different types of enolates. Why? Because it has got two different types of alpha hydrogens. This is our functional group, okay? And this is our alpha carbon. This is one type of alpha carbon, and this is the other type. And on this alpha carbon, we do have one hydrogen, whereas on this one, we do have two hydrogens. Abstracting this hydrogen will result us in one type of enolate, and when you abstract any one of these hydrogens, it will result in the other enolate ion. Let's draw the structure of the enolate ions that will be created from abstracting these different hydrogens. If I'm going to abstract this hydrogen, then this will be the enolate ion that will be created, and this will be resonance stabilized, where these electrons will be coming in here, thrusting those electrons onto oxygen. And in the same way, if I'm going to abstract this hydrogen, then this will be the enolate ion that will be created. And for writing the resonance contributor, we are going to push these electrons right here and push these electrons towards oxygen. So here are the resonance contributors of the two different enolate ions that will be formed from 2-methyl-cyclohexanone when it is reacted with LDA. Now between these two enolate ions, which one will be formed faster? Or which one is the kinetic enolate ion? We can obviously say that this is the one that is formed faster. Why? Because there are two main reasons behind it. This enolate, if you want to form this enolate, then you have to abstract one of these hydrogens, and there are two hydrogens that can be abstracted to give this enolate ion. And therefore, the probability for LDA to go and abstract these hydrogens will be greater with respect to this hydrogen, right? So that is one reason. And the second reason is that if this enolate ion needs to be formed faster, then this is the hydrogen that will be abstracted. This hydrogen has lots of steric hindrance. Say for example, this LDA needs to go and find this hydrogen and abstract it. It will be a little difficult for it to go and abstract this hydrogen when compared to these hydrogens. So we can say that this is the kinetic enolate ion, which is formed faster. The other enolate that is formed from the reaction is basically a thermodynamic enolate, which is basically the most stable enolate. Now, why this should be called as the most stable enolate? Why? Because when you look into the double bond here, there is more substitution across the double bond. The same rule that applies for the stabilities of the alkenes can also be applied here. The more substituted alkene is the more stable alkene, and in the same way, the more substituted enolate is the more stable enolate. Now between these two enolates, which one is highly substituted? You can see that there is one hydrogen here, but there is none here. So therefore, this should be the most stable enolate. So we have said that this is going to be our thermodynamic enolate. Now each of these enolates will react with alkyl halide to give us the alpha alkylated carbonyl compound. So these electrons will come in, and then it will go and attack this electrophilic carbon, thrust these electrons onto iodine. So here is the product obtained, and you can see that this alkyl group was there to begin with. And this is the new alkyl group that we have added using the enolate ion. In the same way, we can also write down the other product. So these electrons will come in and it will go and attack this electrophilic carbon, thrust these electrons onto iodine. And one of these alkyl groups was there to begin with. And here is a new alkyl group that we have added. So this would be the kinetic product. And this is the thermodynamic product. What would be the relative amounts of these products formed in the reaction? That's going to depend on the reaction conditions. If you conduct the reaction at a lower temperature, say for example at minus 78 degrees Celsius, then it would be the kinetic product that would be formed. But if you conduct the reaction at relatively high temperatures such as 25 degrees Celsius, then it's going to result in thermodynamic product.